Okay, so we're going to finish chapter 10, which is the last material for the block. So we ended the first half of the lecture talking about vapor pressure. And this is just an equation that allows you to calculate vapor pressure as a function of temperature. So we talked here about the fact that vapor pressure is always going to go up with temperature. And when you look at this, the slope is related to the delta H of vaporization, which is always positive. So we're going to see when we see the equation that will make it true that vapor pressure itself is always bigger at a bigger temperature. I guess we will use this equation when we're in lecture together. So there isn't a slide that goes over a problem or anything, but I'll show you how to use this equation. ln is natural log, so you might need a little refresher on how to do that on your calculator. And this is just a table of vapor pressure of water at various temperatures. So it's always true that vapor pressure goes up with temperature. And that's also true that the vapor pressure of water, if they had other substances on here, you'd notice was lower than most other substances because the intermolecular forces hold water in the liquid phase because they're so strong. So water has a fairly low vapor pressure. Okay, so now we are looking at different substances. So the graph on the left is vapor pressure versus temperature. Notice that ether, which is a carbon compound with one oxygen in the middle, and it's nonpolar. Ether has a much higher vapor pressure than water because the intermolecular forces are so weak. Ethanol has one hydrogen bond on one end, so it's CH2OH, and so it's able to hydrogen bond, but not as much as water. Water has the ability to have two hydrogen bonds. So water is going to have the lowest vapor pressure at the same temperature, ethanol slightly higher, and ether even higher. And this is just for any substance, a plot of vapor pressure versus, or natural log of vapor pressure versus 1 over T is going to be a straight line. So if you look at this equation, it has the general form of y equals mx plus b, where y would be natural log of vapor pressure. The slope is going to be related to the delta H for the substance. And what you're graphing as x is 1 over x, or 1 over T, sorry. So 1 over T, our natural log of P versus 1 over T is going to be a straight line. So there are lots of different types of solids, and amorphous solids are where particles are randomly arranged and have no order or long-range structure. An example is rubber. Another example is old glass. Crystalline solids where particles have an ordered arrangement extending over a long range, things like ionic solids, molecular solids, covalent network solids, and metallic solids. So this is just a couple pictures of those, a crystalline one on the left, an amorphous one, rubber, on the right. So types of crystalline solids and their characteristics. So if it's ionic, you have ion-ion forces holding it together. It's usually pretty brittle, hard, takes a lot of energy to melt because you have to break the ionic bonds between all the different ions, cations and anions in a substance. Molecular, you either have dispersion forces, dipole-dipole, or hydrogen. They tend to have low melting points, easy to break them apart into molecules. Give some examples: water, bromine, carbon dioxide, methane. Network covalent, very, very hard, very, very high melting, something like diamonds, the hardest substance there is. So we'll see that that's because it's actually one huge covalently bonded molecule. Same thing with sand, SiO2, silicon dioxide. Metallic bonds have varying hardnesses and melting points, and they conduct electricity. So there are lots of different examples of metallic solids. Ionic solids, this is the only slide we're going to look at for ionic solids. But if you look at it there'll be a few things you can understand. Number one, there are tons of bonds between cations and anions in a crystal. So it's not just a molecule of sodium chloride, it's a huge crystal where a sodium sees a chloride, which sees another sodium in this big pack. And the things that will determine the structure of the packing, if you have, will be the sizes of the cations and anions, and then the charges on them. So if you had a doubly charged cation, it would pack differently. If you had really large anions, it would pack differently than this. So those are things that will determine the packing. So this is a picture of just a molecular solid. So it almost looks like a network covalent, which we'll talk about it in a minute, but it's not. So this is a picture of a whole bunch of water molecules, all hydrogen bonded. So there's a lot of structure to it. It's an example of ice. So covalent network solids look similar to this, but they're not hydrogen bonded. They're actually covalently bonded. So if we look at, they should give a better picture than that. I'll have some models in class to understand like the difference between carbon in the form of diamond and carbon in the form of graphite. But essentially what you have, and it's not that easy to see, but you just have a huge molecule. So when we look at diamond and graphite, those will be the best examples. I think there are some good pictures in your book, but I'll also bring some three-dimensional models. Metallic solids particles are metal atoms whose whose core have, I can't read the word that's under my picture and it doesn't make sense to me, but they have metallic properties such as they conduct electricity. So an example is iron. So it's essentially all of the nuclei together and the electrons are in a big orbital so that the electrons can flow over the whole system. Oops. And so we are going to skip sections 7, 8, and 9, which talk about how you determine the properties or the structures of solids. And we're not skipping it because it isn't important, but it's just a little bit too much in this chapter at this point in your career. If you take geology or an inorganic chemistry class, you'll learn more about this. So I'm going to skip all the slides that go with sections 7, 8, and 9. Okay, so this is now going back to covalent network solids. So allotropes are different structural forms of an element. So diamond has a lot of different forms. You have graphite, diamond, fullerene, nanotubes. So carbon as a solid can be many different structures. So, okay, good. This is some of the pictures that I wanted you to see. So the top one is of graphite, where it's not too easy to see in this picture, but you have many sheets. And within those sheets, the carbons are sp2 hybrid orbitals. So you have sheets that are flat, and then there are London dispersion forces holding them to another sheet. And that gives you the properties of your pencil lead, which is actually graphite. It's pretty easy to pull those sheets away from one another and move it onto a sheet of paper because it's London dispersion forces. Whereas diamond, each and every carbon atom in a diamond has sp3 hybrid orbitals. And so you have a structure where every single atom is actually bonded to 4 other ones, which make it a huge molecule. So if you have a diamond ring on, it's one single molecule. All the carbon atoms have 4 sigma bonds to other carbon atoms. These are some more pictures. So fullerene is a circular structure of how the carbon atoms are all bonded, and carbon nanotubes are more like the sheets that I talked about in graphite, but then they form tubes rather than forming sheets relative to each other. Silica, which is sand, is another network covalent. And if you looked at the picture, it looks much like diamond in that everything is covalently bonded together. So you have a huge molecule essentially when you make glass. Okay, I think this is the last thing we're going to talk about in the chapter, and that is about phase diagrams. So we can do experiments to understand where things melt and where things vaporize and get an understanding of when a material might be useful. Because if a solid melts at a temperature below something like you're building your car engine for, then it wouldn't be useful. So understanding when things are solid, liquid, and gas is very helpful if you're a materials scientist. So this information can be all summarized onto a phase diagram that shows you the relationship between pressure and temperature when you have different phases. So notice you can have solids, liquids, and gases. As you go up in temperature, you're going to be more likely to have gas in the middle temperature range, liquids and solids. As you go up in pressure, you tend to stay within the same phase. This shows a few important points. The triple point, so there is one set of pressure and temperatures, one point where you can have all three phases in equilibrium together. Notice any place else on the lines you see that separate phases, like between liquid and gas, any place on that line you can have liquid in equilibrium with gas. So there are many, many combinations of pressure and temperature. Same thing for the phases between, or the boundaries between solid gas, solid liquid. So the normal boiling point is the boiling temperature at 1 atmosphere pressure. The critical point is a unique point where above that pressure and temperature, you can't have a phase transition. So you have what's called a supercritical fluid. Notice there's no line, so you wouldn't see any break in your cooling curve. So these are just some of the things I just said. The normal boiling point, the temperature at which boiling occurs when there's exactly 1 atmosphere of external pressure. Normal melting point, the temperature at which melting occurs when there's exactly 1 atmosphere of external pressure. The triple point, point at which all three phases coexist. The boiling point by definition, talk about it. Boiling point, the reason why boiling point depends on pressure, external pressure, is because the boiling point is the temperature at which the vapor pressure of a liquid is equal to external pressure. So it makes sense that at higher temperatures, the gas has a higher vapor pressure. And so the temperature at which those two are equal is going to be different. So the critical point, it's a combination of temperature and pressure beyond which a gas can't be liquefied. So there will be no phase transition. The critical temperature, the temperature beyond which a gas can't be liquefied regardless of the pressure. And the critical pressure, the pressure beyond which a liquid can't be vaporized regardless of the temperature. So above that, you have something that's called a supercritical fluid. It's a state of matter beyond the critical point that's neither gas nor liquid, it's a fluid. And the reason this happens is, if you think about it, as you increase the temperature, so if we enclose some liquid in a closed container and we increase the temperature, as the temperature goes up, the density of the gas will go up because the vapor pressure will go up, but the density of liquids go down with temperature. And so you're going to reach a temperature at which the density of the liquid is the same as the density of the gas. And then you can't distinguish those two phases. You have what's called a supercritical fluid, and you no longer have a liquid and a gas. So these are just some examples of phase diagrams, which we'll spend a lot of time talking about in class. The important features like the slope of the solid liquid line, whether it's positive or negative. This one for water, the solid liquid line has a negative slope. We'll discuss these examples in class in great detail. This is just a picture of making water at the triple point so that you, in that container, have liquid, solid, and gas. This is an example. If you go back here, water is unique, and because that line is sloped a little bit to the left, if you have a solid, let's see, no, if you have if you have a solid and you increase the pressure, so if you have a solid, you're at some point and you go straight up in pressure, you're going to force whatever it is, in this case water, to melt if that solid liquid line is sloped to the left. So that's what this is showing you. You're increasing the pressure by having these two weights in a wire. And so the wire is starting to melt through that ice because at a higher pressure, the solid goes into a liquid. Whereas if we look at CO2, it's going to be exactly the opposite. If you had CO2 and you increase the pressure, went straight up, you just keep it in the solid phase. So if you had a chunk of CO2 and you put this weighted wire on it, it would not melt through the CO2 because it would just force it to stay in the solid phase. And that is the end of that chapter. We'll talk a lot more about things in class, and that's the end of the new material for Chem 107.